Hi and welcome to the class of real analysis, and today we are going to discuss on a very important topic, that is Bolzano Weierstrass theorem for sets. And later on we will see a theorem of Bolzano Weierstrass for sequence of numbers. So the theorem says that every bounded infinite set has a limit point. So first of all, we all should be familiar with the limit point, that what is a limit point, what is a bounded and infinite sequence. So we already talk about these words, bounded, infinite, and limit point. So the bounded sequence means that the sequence whose infimum and supremum exist. So it's bounded below and is bounded above. So if we have a set S, then if it's bounded, so its supremum and infimum exists. Just like in this case, we can see we have this sequence 1 over n such that n belongs to n. So if we draw this set on a real line, we already know, we have done this a lot of times, that if we draw a line like this and we plot the points, so somewhere here we will have our 1, and then 1 over 2, 1 over 3, 1 over 4, and so on, and eventually it will uh, stop at 0. So 0. So this set is bounded between 0 and 1. So we can say that this set is bounded, so its supremum exists and its infimum also exists. So that's the definition of bounded. And infinite, by infinite means that there are infinite terms. So here we can see that there are infinite terms. So any set that is bounded and is infinite, so it has a limit point. So now, by the definition of the limit point or accumulation point, we already talked about these definitions in the previous classes. So we can again check the definition of the limit point here. So we have the definition of limit point and accumulation point. So this is the definition that we discussed. A point x belongs to R, so limit point is not necessary that it should belong to the set. It should belong to R. It may be in the set, it may not be in the set. So it belongs to R, that is a set of real numbers, is a limit point of a set E if for all epsilon greater than 0, the set x minus epsilon comma x plus epsilon intersection E contains infinite many points. So we already know what we mean by this definition. So the intersection, that if we have a point x, we will call it a limit point if this x plus epsilon comma x minus epsilon with the intersection of the set E itself is infinite. So we call it a limit point. Okay, so actually the neighborhood of this point, this is the neighborhood of this point. We can say that this is the neighborhood, this thing here, this interval is the neighborhood of this point x, and the intersection of this neighborhood with E, that is a set. So for example, this is our set. As an example, we can write that this is our set. Then we can write that we can take any element in this set and we can check whether x plus epsilon and x minus epsilon with the intersection of the set itself is infinite or not. So this condition should hold for the limit point. So we call it a limit point. So that's the definition for the limit point. Now we'll start the proof. So we'll start with the assumption that we will take a set S and its bounded subset of R containing infinite number of elements. So it's given in the statement that the set is bounded and infinite, so it has a limit point. So since the set is non-empty and it's bounded subset of R, then there exists. So why I call it non-empty? Because we know that it contains infinite number of elements. So if the set have at least one element, then we call it's a non-empty set. So here we have infinite elements, in fact. So since S is non-empty bounded subset of R, so there exists supremum. Yes, we talk about this thing that if it's bounded, that means that it has supremum and infimum. And then we assume that let A1 represents the infimum of the set and B1 represents the supremum of the set. Okay, so we denote these infimum and supremum with A1 and B1. Then for every x belongs to S, we know that the supremum of the set is the largest value of the set and the infimum is the smallest value of the set. So every element x of the set will be greater than or equal to its infimum and will be less than or equals to its supremum. And this holds true for every element of the set. That is, we can say that this x means every element of the set, that is our set S, belongs to the interval a1 comma b1. So we can write in this form because we developed a relation between x, a1 and b1. So now by seeing this relation, we can just develop this idea x belongs to a1 b1 closed and bounded interval. So now the set S is contained in the closed and bounded interval because this x shows that every element of the set is belonging to this interval. So this interval is closed. We can see this is closed interval. So closed intervals are closed sets. So closed and bounded by a1 and b1. The bounds are also here, a1 and b1. Therefore, we can say that we can call it interval 1. So we can call it I1 equals to the interval a1 comma b1. So up till now, we just uh, develop the scenario of proof, that how we are going to prove this whole idea. So we are just developing a scenario. So now we concluded that this a1 b1, we call it interval 1. Now let c1 be an element in the middle of the interval. So we can write it as a1 plus b1 divided by 2. C1 is the element of this kind, that is a1 plus b1. So we are taking average of these 2 points. So average of these 2 points, that is a1 and b1, and then dividing it by 2. So we call it c1. Then at least one of the closed intervals a1 comma c1. Then okay, if we take c1 like this, then we can say that if we have interval a1 b1, for instance, I will plot on the real line for better understanding. So this is our b1 and this is our a1, and we take the average of this a1 and b1. So c1 is the point, that is a1 plus b1 over 2. So it will be somewhere here in between them. Then this is point c1. Then we can write that the interval uh, uh, a1 c1 and then c1 b1. So this a1 b1 will be contained in the union of this set a1 comma c1 and c1 comma b1. Okay, so at least now this is very important idea, that at least one of the enclosed intervals a1 c1 and c1 b1 must contain infinitely many points. So it's obvious that if we have already a set, that is set S, this is set S from a1 to b1, so it contains infinite number of elements, and we divide, since we divide this set like this into 2 parts, that is a1 c1 and c1 b1. So now we can see that we cannot count the elements of this set, and if we divide the set by this assumption, and we assume that if we have um, some finite elements in one of the part of this set, then obviously we will have infinite elements in the other part of the set. So this is obvious because we cannot count the elements of an infinite set. So that's why we are claiming that one of this interval, at least one of this interval, must contain infinitely many points of S. Otherwise, S would be a finite set. If both the parts have finite elements, then this S is no more infinite, so it will be finite. That's why one of the uh, area of this set, let's say call it area 1 and call it area 2, so at least one of the area will be infinite. Okay, so now we take one such subinterval. Okay, now we call the intervals, one of the intervals will be infinite from these two intervals. Now what we do, we will take one such interval containing infinitely many points, elements of x, and call it I2, that is equals to A2 comma B2. Okay, so we take one of the set. We don't know which one of this interval or the set is infinite, but we assume that we take an infinite interval, an interval that contains infinite elements. So we call it A2 B2. We name it like this, A2 B2. So initially we have I1, that is A1 B1, which is actually the set itself. The set S is contained in this interval, and then we take another interval I2 equals to A2 B2, such that now this interval is very obvious that this is contained in I1. So this is my I1, this is A1, this is B1, and then we break the interval into two parts and we call it area 1 and area 2, and therefore this was C1. So we had two intervals, A1 comma C1 and C1 comma B1. Then we said that one of the interval is infinite, at least one of the intervals is infinite. So we take infinite interval, that is we take infinite set. For instance, this set was infinite, and they both may be infinite. It's not necessary that one is infinite and one is finite. They both may be infinite, but they both cannot be finite at the same time, because we have claimed that the set S is infinite, right? So one of the interval have to have infinite. So at least one of the interval have to have infinite. So we assume that this interval, this area A2 is infinite, and we take this interval and we call it, name it A2 and B2. So we just change the name, so it doesn't matter. We call it A2 and B2, and we can do that. So we call it A2 and B2. All right. And then we can see that this interval which we have taken is actually this area is contained in this whole area. So we can write that I2 is contained in I1. So this I2 that we are assuming here is contained in I1. And then the length of I2, okay, the definition of length of interval is that the length of interval is equals to the difference of the boundary points. So if I have boundary points like this, A and B, so this is interval, that is A comma B, then the mod or the length of the interval will be equals to B minus A. Okay, but here we can see that we have written I2 equals B1 minus A1 over 2. So why we did that? I2 is actually A2 minus B2. Okay, so first of all, we can write that I2 is equals to B2 minus A2. We can write in this way. But B2 minus A2 is actually equals to B1 minus A1 divided by 2. Because this length here is half of this length, right? Half of this length. Why? Because our initial interval was from A1 to B1 and we cut it into half. Here we can see that this was A1 plus B1 over 2. So we take the midpoint. This is the midpoint actually. C1 equals to A1 plus B1 over 2. It was the midpoint of the set. Let me draw here. So if this was my A1 and this was my B1, so C1 was the midpoint. That was A1 plus B1 over 2. Okay, so that's why we can write that this interval I2 and the length of I2 is equal to B2 minus A2, where B2 minus A2 is equals to B1 minus A1 over 2. So this is the, if this is the length for I2, So that's actually half of this length. Okay. So again, now we box it here, b1 minus a1 over 2. This is the length of I2. Then we take C2 and repeat the same process. So this possesses the same qualities as mentioned for C1, that this C2 is the interval. Sorry, it's the point. C2 is the point, that is A2 plus B2 over 2. So let me erase this stuff. I will make some more drawings here. So now we half the interval again. So what we did initially, we have an interval of this kind, that was A1, B1. We half the interval, take point C1. Then we take this interval and name it as A2, B2, and then processed, call that interval 2, I2 equals to A2 comma B2. Then we found the length of the interval. Now we are again halving this interval. We are taking a point C2, that is equals to, now we call this point is A2 and this point is B2. So now we are claiming that it's B2 plus A2 divided by 2. So we are somewhere here in between, in the middle of A2 and B2. So this point C2 is the middle of uh, A2 and B2. So similar manner we can proceed as we proceeded for C1. Now this interval, we can call it that this interval is a subinterval containing many elements of S, and call it I3 equals to A3 B3. We can name it as A3 B3. So now I3 is contained in I2, and then I2 is contained in I1. This is true from the above statement. We already proved it, that I2 is contained in I1 and I3 is contained in I2. So if we break this interval into half and we take some point here B3, so now there are again two intervals. So one of the interval is this one, and one of the interval is this one. So now again the same thing, that one of at least one of them will be infinite. So we take the infinite interval and call it as interval A3 B3. So now the length of the interval I3 will be again it will be B3 minus A3, which is let me just do it like this. So I3, its length is equals to B3 minus A3, which was half of B2 minus A2, and then B2 minus A2 was half of B1 minus A1. So it will be 2 times 2. So we can write it as B1 minus A1 over 2 squared. Okay, so then we'll take C3 and proceed as we did earlier, and we will obtain a family of closed and bounded intervals. So as we get I1, I2, I3, we will get I4 as well, and I5 as well, and so on. And these intervals will be nested intervals, because we saw that I2 was contained in I1, then I3 was contained in I2, and by the property, trichotomy property that we have is sorry, by this property that if one interval is contained in other interval, that is I2 is contained in I1 and I3 is contained in I2, then eventually this I3 is contained in I1. So if every interval is contained in its previous interval, so it is contained in the interval, the first interval, that is interval 1. So here we represent it that I2 is contained in I1, I3 is contained in I2, I4 will be contained in I3, and similarly In will be contained in In minus 1, and so on. So, and the length of this In will be 1 over 2n minus 1 times b1 minus a1, as we have seen here that length of I2, it was b1 minus a1 over 2. Length of I3 was b1 minus a1 over 2 squared. Length of I4 would be b1 minus a1 over 2 power 3. And if we move on, then In equals b1 minus a1 over 2 power n minus 1. So here's the thing. For all n belongs to the natural number, it contains infinitely many elements of S. So their infimum of bn minus an. Now infimum of these intervals, that is b1 minus a1 comma b2 minus a2 b3 minus a3, these all intervals dot 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 is going to be 0. And why this is going to be 0? So let's think about it. Initially we have an interval that is from a1 to b1. We halve this interval and call it that one of them, the intervals will be at least infinite, and we assume that this interval is infinite, and we start working on this interval. Okay, then what we did, we again halved this interval, and again then we suppose that one of these two, okay, this was interval 1, this was interval 2, then we halve this interval 2 as 3 and 4, then we again assume that one of them will be infinite. So let's consider that we assume this is infinite. Then what we did, again we have this infinite interval, and again we make two intervals, and we proceeded this process infinite times. So eventually the length of the last interval will be going to be 0, will be going to converge at 0, because we are doing this and carrying out this process again and again and again, and we can see that the length of interval is going to be smaller and smaller. So this was actually b1 minus a1, this whole was the length of the interval. Then we have b2 minus a2, then b3 minus a3. So the intervals are they are smaller and smaller. Okay, so the intervals are going to be smaller and smaller, and the length of the interval is eventually going to be 0. So the infimum of this all lengths will converging 0, right? Since the intervals obtained are nested, therefore by the nested interval theorem, there exists precisely one point, we call it as x, such that the intersection of all these intervals is equals to x. Okay, let me give an example what is mean by this thing. So for instance, okay, what are nested intervals actually? That the nested interval are simply the intervals that are contained like this, as we talked just now, that I3 contained in I2 contained in I1, and every uh, uh, successor interval is contained in the predecessor interval. Okay, so let's talk about this minus 1 over n to 1 over n. And n belongs to the natural numbers. So the intervals of this kind will be like, first interval will be minus 1 over 1 comma 1 over 1, because this n belongs to natural numbers, so we start putting natural numbers in the denominator. First we will put 1, then we will put 2 in the denominator, then we will put 3 in the denominator, and this process will continue further. So at the end, when we are going to infinity, okay, first thing that we can see that this minus 1 comma 1. So this interval here is contained in this interval, because this is interval from minus 1 to 1, and this is interval from minus 0.5 to 0.5. So these all points are actually contained in this as well. Okay, then again we can see this is contained in this, and again every new interval is contained in the previous interval, and this process goes on and on. So these are the nested intervals. So if we have a nested interval, then eventually when I'm going to uh, infinity, then I am at, for instance, if I say that n tends to infinity, so negative 1 over n is 0, 1 over n is 0. So if I have, for just consideration, I am telling this thing, it's not actually like that, that if I say that n tends to 0, now my interval will be 0, comma 0. So again, if we see here that this 0, comma 0 is contained in every interval. Every interval here, this 0, comma 0 is contained. It's 0 is between -1 and 1, 0 is between negative 0.5 with 0.5, 0 is between negative 1 over 3 and 1 over 3. So every number is from negative to positive, so 0 is contained there, right? So now if I take the intersection of all these sets, so it's going to be 0, or like 0. Okay, we are not considering, we should not consider it 0, because 0 is not the case here, because we are not saying that n is actually equal to infinity. We are saying that n is approaching infinity. So we can say that, let's say that this is from negative x to x. So these all this is contained in these all intervals. So the all intersection of all these open close intervals will be this thing again, because this is the only interval that is contained in all these intervals. So the intersection will be this thing here. So that's mean by that we will have a point x. By the nested interval theorem, we will have at least one point x, that intersection of all the intervals will be equal to the point. So this is the description of this thing. Okay, now what we need to do is, now we need to prove that this x is a limit point of S. Okay, now just the last thing. So let epsilon greater than 0, since the infimum of this equals to 0. Okay, this infimum is equals to 0 of all the intervals, because the length of the intervals, oh sorry, length of the intervals, this is the length of the interval. So infimum of all the length of the interval is 0, because we said that we are cutting the interval, halving the interval again and again, and we are doing this infinite times. So the length of the interval is eventually going to be 0. So the infimum will be 0. So there exists an m belongs to n such that bm minus am is greater than equals to 0 and less than epsilon. Okay, so it means that there is some interval in all these intervals, there is some interval that this is a1, this is b1, we have the interval, then again we have the interval, then again we have the interval, then again we have the interval, and going on. Then it says that there will be some bm minus am, some interval bm and am, some interval which will be such a smaller that, such a smaller that it will be greater than 0, but it will be very, very uh, small, that it will be like it will be converging 0. So for each epsilon greater than 0, let epsilon greater than 0, so it's epsilon is just greater than 0. Okay, it is just greater than 0. So we don't know how much greater. It can be 0 0.000000009, 0 0.0005, like that. Okay, so interval of this kind we will get. So since x belongs to im, okay, now x, the point, will be belonging to this interval. Okay, because this x, we already talk about that we are taking the intersection of intervals a1 comma b1, a2 comma b2, and somewhere here it's am comma bm. And so we have Okay, so since x is belongs to Im and Bm minus Am is less than S, so Im is contained in this neighborhood of x comma epsilon. Sorry, this is uh, Bm minus Am is less than epsilon. Okay, so Im is contained in the neighborhood of x e, that is x plus e comma x minus e. So now since Im contains infinitely many points of x, sorry, the set S, and the neighborhood of x contains infinitely many elements of S, this happens for each epsilon greater than 0, therefore x is a limit point of S. So here we concluded that x is contained in Im, x belongs to Im, and Bm minus Am is less than epsilon. So there are infinitely many points around this x. So the intersection of this x, the neighborhood of x with this Bm minus Am, or the set, sorry, S, will be infinite. So that's what we concluded, and that's all for the time being. Thanks for watching the lesson.